Welcome to lecture 2.5 on the chain rule. This is our next rule, and we will be using this a lot throughout this course. Before we begin talking specifically about the chain rule, which is used for composite functions, let's go back and recall what a composite function is. Remember that most functions in life are actually composite functions, and that is that they're not just simply discrete input and output, that typically a composite functions are functions in a row, and the output to the first function becomes the input to the second function. And so notice here, if we're looking at a composite function f of g of x, remember that what's in the parentheses is the input. So this x goes into g, comes out as g of x, or the y value for function g, which then goes into f of x and comes out as the y value for f of x, or f of g of x. Okay? And again, think about this. I mean, if you're talking about your salary, etc., you work a number of hours. That goes into some pay function. Let's say you get 10 bucks an hour, and then you get your gross pay. And then that goes into some tax and benefit portion that takes money away to get your actual net pay. So that's a typical example that we can see kind of here. I guess I should have hit that first. So your number of hours would go into your payroll, your gross pay goes into taxes and benefits, and you get your paycheck. So let's look at an actual function here. So let's say that g of x is x squared plus 2, and f of x is equal to 2x minus 3. And we're trying to figure out what f of g of x would be. So remember, when you put x into g of x, you simply get g of x out. So this becomes x squared plus 2. But when I put g of x into function f, or f of x, remember that this formula here, this formula g of x, gets placed wherever there is an x. So this becomes 2 times g of x, or x squared plus 2, minus 3. And then we simplify and we get 2x squared plus 1. Okay? So that was a brief review of composite functions from algebra. See if you can find f of x, or is this what we just did? I'm not sure if this is a different one or not. This is a different one. F of x is 3x squared. G of x is 2x minus 1. So find capital F of x, which equals the composite of g of x on f of x, f of g of x. And then once you find that, find the derivative. Okay? Again, this is a good place. You might want to pause and try this. So our function g is 2x minus 1. We are going to put that into f of x wherever there's an x. So we get 3 times 2x minus 1 squared. We're going to FOIL that out, and I get this polynomial 12x squared minus 12x plus 3. Now, I know I've gone through that fast, and again, you can pause. I suggest on all of these you pause first and try them, and then you can follow along listening and watching. All right, so there's our f of x. The derivative of this is pretty easy since we have a difference and a sum. So we can take the derivative of each piece. We have two power terms, and then we have a constant. So our derivative here is going to be the derivative of the first piece, which is 12 times 2x, which is 24x, and then minus 12 times 1, or minus 12. All right. Now we're going to look at the same function again in a minute using the chain rule. All right. Now there's a lot of stuff going on here. So let's look at this notation. So the idea here is that y is f of u and u is g of x. So technically y equals f of g of x, or some composite function. And since that is true, then we know that y is a differentiable function of x. And so y prime, these are just notations, or dy dx, it equals the derivative of f with respect to g of x times the derivative of g of x. Okay? And here we're talking about taking the derivative of the outer function and the derivative of the inner function. Okay? dy du times du dx. And this is one of the interesting things that's happening with calculus here. These are notations. So notice that we first take the derivative with respect to u, some substitution, and then we take the derivative with respect to x. And notice the du's would technically cancel out as a fraction, and we'd get dy dx, which is what we're looking for. Now, I think the notation is confusing. I'm going to use it for a couple of the first problems, and then I'm going to use a more simpler, what I think is a more simpler outer and inner kind of process that you would use to solve these. All right. So we have f of x equals 3x squared, g of x equals 2x minus 1. This is the problem we just saw before. So these are the answers that we got, and here's our derivative. All right. So notice if we make f of u, instead of f of x, we just substitute the u and we get f of u is 3u squared. Remember that u equals g of x, or u equals 2x minus 1. So what we're going to do is first take the derivative with respect to u, which is here, and we get 6u. And then we take the derivative of u with respect to x, the inside function, and the derivative of u, which is 2x minus 1 with respect to x, is simply 2, right? The 2 there, because the derivative of negative 1 is 0. And then the answer is the product of these things, so it's 12u. And remember to substitute u back in, we get 24x minus 12 when we substitute back in 2x minus 1 for u. Okay? Now, if you look at this function, I'm going to jump ahead here. Here is our original f of g of x, right? And so if you use the model I'm talking about, working from the outer to the inner, notice that what you have here is a power function on the outside. You have the constant, which we can use at the end. So notice we have something raised to a power. So what I get here is I drop the power down, right? So I get 6 times 2x minus 1 to the 1 power. 6 times 2x minus 1 to the 1 power. That's the derivative of the outer. And then the derivative of what's inside the parentheses is just 2. And when I multiply that out, I would get the same thing, 24x minus 12. So it's probably hard to follow along audio, oral, what is that? By sound versus by sight. I'm a much more visual learner than audio learner. Okay, so again, here's where I'm talking about take the derivative of the outer times the derivative of the inner. So the chain rule is like using silverware at a fancy restaurant. Start from the outside and work your way in. Okay, so notice here a radical. We have y equals x squared minus 1. Find dy dx. So the first thing I want to do is try to identify the outer function and the inner function. The inner is usually, this one's pretty simple because again, if I change my radical to an exponent, and also with the radical, I can see what's inside the radical is x squared minus 1. What's outside the radical is just the radical, square root of. And so I get y equals the square root of x squared minus 1, using colors to demonstrate the outer and the inner. So remember, my answer is the derivative of the outer times the derivative of the inner. Okay? So the derivative of the outer is simply u to the 1/2, right? Or, that is what square root of u. So the derivative of that piece is 1/2 u to the negative 1/2, or 1/2 times the square root of u. The derivative of the inner is just 2x. So I multiply these things, and I get 1 over this 2 times the square root of u times 2x, or 2x over 2 times the square root of u, or x over the square root of x squared minus 1. Okay? Now I went through that very fast. And if I was writing this in worksheet, I would rewrite this as x squared minus 1 to the 1/2 power. Okay? And so what I would get is something like this. 1/2, if I did the outer first, 1/2 times x squared minus 1 to the 1/2 minus 1, which is negative 1/2, 1/2 x squared minus 1 to the negative 1/2 times the derivative of what's inside 2x. Okay, let's look at another one here. Oh, let's look at a whole bunch. So notice here, and again, here's a good place to pause. The outer is the square root and the inner is the sine of x. Okay, and number 2, wait, that's a quotient. And you could use the quotient rule, but notice that what I can do when I have 1 over a function, I can make this z squared plus 1 all raised to the negative 1 power, and then I have an outer and inner. Here, the outer function is the cosine. The inner function is a cubed plus x cubed. And remember that a cubed is considered to be a constant, or a is a constant. And this number 3 is asking you to find the first and second derivatives. Oh my gosh, look at number 4. So here we have, let's start from the inner. Our inner is 3x squared. Our middle, or our second inner, is sine. Our third inner, or middle, is cosine. And then look, we have an outer function, which is squared. So this has actually 4 levels. And so we just do outer, and then the next one level in, and the next level in, and then our 4th level in. And you're probably going, what the heck is going on? But truthfully, once you start doing these, and you've done a couple, maybe about 5 or 10 of these, they actually aren't so bad. So like here I can see this is 1/2 sine x to the negative 1/2 times the derivative of sine x, which is cosine x. 1/2, well, there's no steps there, is there? Whoopsie. So again, the outer here is the square root, or 1/2 u, or excuse me, u to the 1/2. So when I take this, the derivative of this, the derivative of the outer is 1/2 times the square root of sine x, which is what you see there, to the negative 1/2. So it goes in the denominator, times the derivative of sine x is cosine x in the numerator. Here I get, if I rewrite this as z squared plus 1 to the negative 1, I get negative 1 times the quantity of z squared plus 1, and then the derivative of this part inside is 2z. So I get negative 2z over c squared plus 1 to the negative 2, or it goes in the denominator. Here I have the outer is cosine. The derivative of cosine is negative sine, and the argument stays the same. And then I take the derivative of what's inside, which is just 3x squared. And because I had the negative on the sign, it becomes negative 3x squared. Now let's look at this guy. The first one is 2, remember he comes down in front, times all of this to the 1 power, times negative sine of sine 3x squared. Next level, times cosine of 3x squared. Next level, 6x. Oh, I forgot I didn't do the second one there, but you can look at that and try to work that out. Oops, where did that guy go? That's most strange. I don't even have that answer there. I'm not sure why. I apologize for that. And if you want to email me, I'll send it to you. All right. Remember that the chain rule can be thought of as a product of fraction where we're taking the derivatives and factoring out or canceling out. When we're doing word problems and we read them, often we get to this place of being totally confused because there's so much data. So when I read this, it says the relationship between the length in meters and the weight in kilograms of a species of fish in the Pacific Ocean is given by W equals 10.375 L cubed. The rate of growth in length is given by dl dt, 0.36 minus 0.18 L, where T is measured in years. Determine a formula for the rate of growth in weight, dw dt, in terms of L. And if a fish weighs 30 kilograms, approximate its rate of growth in weight using the formula found in Part A. But notice all this is saying is that as a fish grows longer, it's getting heavier or vice versa. The relationship between the length and weight of a fish is equal to the weight equals 10.375 times its length cubed. So all this is saying is as a fish grows long, it's getting heavier. Pretty intuitive. All right. So we have dl dt. We have a formula for w that we can um, differentiate, and we're looking for dw dt. So a lot of these word problems, if we think back to this fraction, we have w, we're looking for dw dt. So if we differentiate this equation, we get dw dt equals the derivative of w with respect to L, dw dl, so we can take the derivative of this equation with respect to L, and then times it by dl dt, and notice what we'll have is dw dl times dl dt, and the dl's will cancel out. All right. So so this is easier to see here. If I take the derivative, I'm looking for dw dt, so I'm trying to evaluate the original equation for dw dt. Notice this equals dw dl, which is the derivative of this equation, times dl dt, because the dl's will cancel out. And dl dt is another formula that was already given to us right here. It's already figured out. So I'm just going to plug that in. So notice if w equals 10.375 L cubed, then dw dl, taking the derivative of w with respect to L, is simply a power rule, right? 3 times 10.375 L, and the exponent is dropped by 1, so I get this here. So now I'm just going to multiply those two parts, dl dt, given in the problem, dw dl, which we just calculated, and I get this formula. So it's not quite as bad. Now I've walked through that pretty quickly, but it's based on this whole concept of really kind of notation that can be used as ratios or fractions so that we can cancel out parts and actually find the answer. Okay. So now the second part of the problem just asked us if the fish weighs 30 kilograms, approximate its rate of growth in weight. So this is asking us to find dw dt to figure out how fast it's growing when the fish weighs 30 kilograms. Now we have a problem again because our formula dw dt is in terms of L, and here we were given the weight, not the length. So we actually need to figure out the length. But remember, wait, we have a formula, right? That was given to us as well. We can figure out the weight of any fish, given its length, by just plugging it into this formula. So I get that the weight of the fish is 10.375 times its length cubed. Its length is, what did we just say its length was? I'm sorry, the weight is 30. We can figure out the length if given the weight. So we get 30 equals 10.375 L cubed. We divide by 10.375 and then take the cube root. And we get that its length is 1.4247 meters long. That's a pretty damn big fish. All right, but it did weigh, I guess, 30 kilograms. That's 1.5 meters almost. That's like a 4-foot fish. All right, once we have that, then we simply go back and plug it into our derivative that we found in part A. And we get that the fish weighs, or excuse me, not the fish weighs, it's changing at 6.542 kilograms per year. Okay? And we know that it's kilograms because that's what the weight was given to us in, and we know that T is measured in years. So it's important that you understand how to find the units as well. Okay? So we've done several of these where the outer function is a power and the inner function is some other function. So this really isn't a special case. We've been doing these all along. The square root follows this, right? Because the square root of a function is equal to that function raised to the 1/2 power, which is, again, a power function. All right. So again here, to me, these become the more I do of these, the easier they get. I pull the 6 down front, I multiply what's inside and drop the exponent by 1, so I get 6 parenthesis x squared minus 4x parenthesis to the 5th power, and then I take the derivative of what's inside. Okay, now, I don't like the way I've separated it all here, and the derivative of what's inside is 2x minus 4. Again, hopefully by now you're getting better at these. And so I can simply apply the power rule. I get 6 times what's inside raised to the 5th power times 2x minus 4. This doesn't seem like a special case, but they say it, so we'll let it slide. Again here, and this is better now you can see the steps. Notice I can do this as a quotient function, or I can rewrite it as 4 times the denominator raised to the negative 1 power. The outer function is 4 times the whole thing to the negative 1, so the negative 1 comes in front. I get negative 4 times 3 squared plus 1 to the negative 2, remember, negative 1 minus 1, and then times the derivative of the inside, which is 6q. So this is pretty straightforward, and then I've just simplified it here. Outer derivative times inner derivative. And many of these